All right, more examples, more setup. I'm letting you work out the details because that's how you're going to learn. Otherwise, you just copy down symbols. So what can we do? We had this beam up at an angle. Classic, simpler example because the angles aren't as hard, but the only difference is just do the angles, do the geometry. There's a horizontal rod. You can do this, right? See if that'll hold. Yeah, that's good. Same force. That's still good. Kind of surprised. Not good. And you can have it down at an angle, right? So we can look for that static equilibrium. Just take it one by one, divide and conquer, and then even if you don't get it right, you've shown that you can do this stuff and you know a lot. So that's kind of neat. We can do cases of rotating things that are not in static equilibrium, but they're dynamic, and we can rotate. This is like gears. So you can have, let's see, a smaller radius, more or less torque. You get less torque, right? Less lever arm. Larger radius, more torque. Larger radius, more torque. Okay, so gears are interesting, and we can relate the amount traveled to the amount around, which might be a good video for another time. I can change the rotational inertia, moment of inertia, by what? Moving it out. That gets harder to accelerate the object. Okay, so those are cases that are fairly simple. Again, using the same structure, but then alpha might not be 0. We can do another kind of cool setup. Try to look at this. Let's see if we can check this out. Think about this one. This will make your head hurt. What do? Well, do like the ancients. Draw pictures. Draw angles. See what you got. Prediction. What direction will this go if I pull to the right, but look at the spinning? What's going to happen? I mean, if I pull this, watch the spinning. So, what direction is it going to move then? Let me roll that guy up here a little bit. What direction will that move? So again, we're getting to the place where sometimes our intuition gets messed with, and sometimes it doesn't. So which way will it move? Make a prediction, be bold, think about it. Now watch. Pretty neat. Watch this, ready? So if I pull that way, it goes that way. That kind of makes sense, right? But why? What about, how about if I pull up at an angle? So there's some angle where it goes that way, some angle where it goes that way. There's probably an angle where it doesn't go either way. Can you calculate it? Oh, my head hurts because you can't see to the end of the problem. Do it one by one. Force analysis, torque analysis, put the forces in, free body diagram, and see what you can do. Just a little puzzle for you. All right. Other things you can do. Well, you can take your Brenner torque demonstrator. Beautiful little piece here. And you could hang things from these guys, and you could balance it, and you can have different lever arms. So you could just draw it, make up your own problem. Here you go. You can have angular acceleration one way, angular acceleration opposite the motion, so it'll be slowing down. You can have static equilibrium. You can find that, measure angles, things like that. So that's pretty cool. That's good. And the one that I wanted to look at real quickly is setting up the ladder. So setting up the ladder, here's a ladder. It's a real ladder. You need to be careful. Generally, the angle of the ladder that you want is so you can stand vertically. So the ladder goes from your toes to your hands. My arms are a little long, so I do it this way. And so I can walk up a ladder, and I can keep my body vertical. And as we walk up this ladder, and we stay vertical, our body, our feet, touches the ladder, which torques the ladder. hopefully still in static equilibrium. Of course, mg, all the pieces of Earth pull down on us with this mysterious non-contact force. But that should be balanced by the force on us from the ladder. And so we can say that the ladder experiences an mg straight down. And of course, there's an mg on the ladder itself, somewhere at the center of mass, which looks like it's going to be a little lower than the center here, somewhere in here. And of course, you know, the way these puzzles are done, we give you just enough information, and you find the rest. So I draw this picture of the ladder. Here's the steps. Select your object. So again, you can draw the ladder. You can draw it any which way. Let's put it over here, just to be fun. And we've got a wall, and we've got a ground. So I'll call this the ground, and I'll call this the wall. Innovative, I know. Then we draw the ladder. Draw it as just a straight line. You don't want to have the ladder like this. Hopefully your intuition shows you that that's going to slip. That's dangerous. You want it more like that. Right? So do that. But in our pictures, sometimes we want to make sure that we can really see it. So here's our ladder. If this becomes easy for you, you are getting good, because it's not easy for most students at first. All right, so there's my ladder. And that's pretty steep. I'm not really happy. I wouldn't feel comfortable with that, but I'm going to draw it just because it's easier to see the angles. And then we have you. What color do you want to be? All right, you are blue, because you've got exams coming, so you're a little sad. There you are. You need a painter's hat. Okay, cool. And better hold on to the ladder. All right, fine. And whatever. Then you might have a dog, or you might have a paint can hanging over there. You know, physics professors are evil, really. So what do? You do this, and you go, all right, okay, fine. I know that I'm going to have to do this kind of game. I'm going to look at my object, clearly the ladder. I'm going to take the forces on the ladder, right? For every force, I need the torque, and I need the Fx and Fy, probably, unless I can just solve it here. So I look at this guy, oh, well, that means I need a free body diagram. I jumped ahead, didn't I? Well, that's fine. Let's see, at the ground, where are the forces? It's a surface, so really there's grooves, and we break them into a part here, force. We're saying it's static. Fs max? I hope not. If it is, then of course that's equal to mu s n on the ground. Oh, by the way, n on the ground. That's that way. N of the ground. Now why do I need to subscript it that way? Well, even here, force of the ground, static friction. Fine, that's it. Where else is it touching? Because it's touching up there, so maybe I want to do a different color to get the... Clearly the wall is pushing this way, so I got the end of the wall. If it were to slide, it's this way, so it's probably pushing up. Hopefully the wall isn't pulling down on the ladder. That would be an evil wall. F of the wall, static, or static of the wall. Hopefully not max. That is mu s n, right? In fact, to be safe, we often let this be, you can read that, 0. I mean, that friction is helping hold up the ladder, but if you do your analysis and you can stand there without any friction, that's safe, right? So anyway, you may or may not have that. Then you've got the force of gravity on you, and then the contact here, but we can just do m of the painter, G, and then we've got m of the ladder, wherever that is, that'll likely be given, m of the ladder, G, and I've got all the forces. Then I just list them, bam, 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 super quick. Right? I'm not thinking too far ahead. That's what makes people so slow, is to think too far ahead. And then you take them one by one. But wait, I'm missing something. Okay, I know that these guys are going to be horizontal plus x, and vertical plus y in cases like this. So fine. But what about this? Where's my axis of rotation? Anything can be used, but you choose a good one. So what do I get rid of if I choose the torque here? Or excuse me, the axis of rotation here? What's not torquing or exerting a force around that point? Any force whose line of force goes through the point. This is going through the point. That's not twisting around, torquing. This is going through. So then I'd have the torque here 0, and the torque here 0. I get torques over here, and we're happy. I could do this one, and I can get rid of these guys. Different equation. I could do anywhere you want, but you might as well make your algebra easier. So I'm going to choose this one. And then you might say, hey, which way? I'll call that plus and minus, but you don't have to. Fine, now that's clear. Plus, minus around that. Then I'll go about getting the torque from each of these guys. Real quickly now, let's just take a look, and you should write it out, because that's how you're going to learn. Oh, maybe you want this stuff, and you say, well, I just got rid of it over here. Yeah, but as you know from last time, they will show up over here, and the algebra will save the day. So we go about this and we say, hey, can I do this? Of course I can. One by one, I divide and conquer. So I look at, say, that force. What's the torque of that force around that thing? How do I do this? Well, I do R. I could do R. I could do R perpendicular. I could do F perpendicular. R is from the axis of rotation that's chosen to the point of application. That's R. Then the line of R and the line of F make this angle. I don't know what's given. I might be given that length. I might be given that length. Just work the geometry. Who knows? So the angle between those lines, you can either use that or that. As we said, either one's fine. You could use R perpendicular. That's from the axis of rotation, perpendicular to the line of F. Okay. So the R perpendicular, let's make that purple. R perpendicular, right? Or you could do F perpendicular to the line of R, right? This, how much of this is going around or tangent to R? Well, then any of these ways, then you'd have to look at this part and break it into a right triangle. Here's the part of MG that's going around A, if you were just letting it do that. Any of those would work. What's best? I'm going to tell you that's going to usually be a pretty good length, that you're going to know that from these other lengths. You do this exactly the same way. How do you do this guy? Well, again, one by one. You say, here's the force. Here's my line of force. My R is, see it? Okay, there. My R is from here to the point of application. Where's our perpendicular? From here, shortest distance to that line of force. There's my R. Hey, that's probably given. That's cool. And then, so, you know, whatever, put it in plus or minus. If I just did that, I'd go around the plus way, right? This would go minus, minus. This goes up there. So then what? But don't use memory. Train your awareness. So now I got this guy. Where's the line of force of this one? Where's R? Where's R perpendicular? You could do F perpendicular, but not so, you know. What's F perpendicular for this guy? Well, it's perpendicular to R, so it'd be that much, right? But I don't see that as well for this one. So anyway, practice, practice. It will click, and all of a sudden you just take it one step at a time, and knowing that all answers to life will be revealed through algebra. Brownie points for the math teachers. All right, cool. I think you're good. See ya.